Let's talk about single slit interference. Now, if I were you, I'd already be upset and a little mad. Single slit interference. Wave interference, is by definition multiple waves overlapping at a single point. So how could a single slit ever produce multiple waves that could overlap? I mean, when we had a double slit, if I put a barrier in here and we have a double slit, at least then, okay, I send in my wave, it gets over to here, there's a small hole. We know what waves do at a small hole. They diffract, which is to say they spread out. At least with a double slit, you would have two waves spreading out. Now they can overlap. Interference. But for a single slit, how are we ever going to get this? Well, I never really told you what. Why do the waves spread out at a hole? Why does diffraction happen at all? Why, when waves encounter a hole, do they spread out? And the answer to this question is the key to single slit interference. And the answer to why they spread out at a hole is something called Huygens principle. And I can't say it. This is a Dutch physicist, scientist who figured this out. Huygens principle. And I apologize right now to all the Dutch people out there. I'm butchering this name. Huygens principle, easier to spell than to say. What he said, he figured out something ingenious. He figured out this. If you've got a wave coming in with these wave fronts, remember these wave fronts are like peaks, and in between them are the troughs or the valleys. If you've got a wave front coming in, propagating this way, you could say, yeah, that wave front moves from here to there. That's what it does. Or he realized with a wave, you could treat every point on this wave as a source of another wave that spreads out spherically, if in the forwards direction. This wave spreads out spherically, this point here. He said that a wave front you can think of as an infinite source of waves. Each point is the source of another wave, and you're thinking, this is horribly complicated. What? What kind of mess is this going to give you? Well, if you add this up, these are going to interfere with each other, constructive, destructive, in a way that just gives you this same wave front right back. This is crazy, but true. If you let every point on this wave be another wave source, it will just add up to another wave front here. You'll just get the same thing back. And this is the key to understanding why diffraction happens, is because the wave was already diffracting, so to speak. It was already doing diffraction. Every point on here was doing diffraction. It's just it always added up with the other waves around it at every other point and gave you the same wave back. But when there's a barrier, when there's something in the way, these here can't rejoin up with their buddies. You just get this one here spreading out, and then this one down here spreads out. All the rest of these get blocked. Now that these are blocked, they're not going to get to interfere constructively and destructively with these points here. And so what do you see when it hits the hole? You just see this thing spreading out. So it was always diffracting, so to speak. We just didn't notice it because it always added up. When you've got a hole or a barrier, that's when we actually notice it. And this is the key to single slit interference, because if I get rid of all of that, if we imagine our wave coming in here like this, well, this wave's going to hit here. Every point's the source of another wave, so this point's going to start spreading out. This point's going to start spreading out. When we have a single slit, we really have infinitely many sources of waves here, and since some of them are blocked, we could see an interference pattern over here on the wall because these can interact and interfere with each other. What interference pattern are we going to see? Well, on the wall over here, we see a big old bright spot right in the middle. And if I were guessing, I would have thought that was it. Big old bright spot, because you shine a light through a small hole, single hole, you'll get a big bright spot there. The weird thing is, this jumps back up, goes to a minimum, a 0 point, and then it jumps back up, and then it comes back up again, and you get this. These are going to be not very pronounced. These aren't very pronounced. You get a big bright spot in the middle. These are relatively weak compared to other interference patterns that we've looked at. And down here, jumps up a little bit, again, over and over here. So this is the pattern you see. How can we get this? How do we analyze it? That's what we're going to try to figure out. To figure that out, okay, well, this is I said there's infinitely many sources here with when this wave gets to here. That would take a long time to draw. I'm going to draw 8. So let's say there's 1, 2, 8 sources. Let's just imagine there's 8 here to make this a little bit easier to think about. And the weird part is that this jumps back up here. So let's look at this minimum right here. Let's look at this point where it goes to 0, this destructive point. So the wave from this topmost point, this wave from the topmost, uppermost point has to travel a certain distance to get there. I'm going to also look at the 5th one down, this one that's basically halfway. How about these two? If these two interfere destructively, the argument I'm going to make is if these two interfere destructively, all the rest of them are going to have to interfere destructively. Why? Well, we know how to play this game. Let's draw our right angle line here. There we go. And so we know that, okay, if these are going to interfere destructively, this is the extra path length. This extra path length that this second wave, this lower middle wave has to travel, has to be what? If I want destructive over here, it's got to be a half wavelength, 3/2 wavelength, 5/2 wavelength. That's how much it's got to be in order to be destructive. So if this is the first point, let's just say that's 1/2 of a wavelength. And what's the relationship between the angle that this is at on the wall compared to the center line? Well, we already figured that out. Remember, that relationship was d sine theta equals the path length difference between these. That we derived. The screen had to be very far away compared to the width of the hole. But that relationship still applies. What would d be in this case? Now we have to be pretty careful. We have to be careful because this hole has a certain width. We'll call that width w. So if this hole has a certain width w, how far apart are these? These are not w apart. These are w over 2 apart. And so what's the relationship here for the path length difference between these two? Well, if they're w over 2 apart, I'd have d sine theta as the path length difference. So d would be w over 2 times sine of the angle that this makes to this point on the wall. And if their path length difference is lambda over 2, then that would be destructive. So equals lambda over 2. And this is a little weird already because, look, I can cancel off the 2's. And what do I get? I get that w, the width of the entire width of the slit, times sine of theta equals lambda. This is giving me destructive. Remember, before, all the points that were integer wavelengths were giving me constructive. This time it's giving me a destructive point over here. And the reason is we played this game where w is the whole width. These are only w over 2 apart. That 2 cancels with that 2. Okay, but I haven't really proved that that they should all be destructive yet. This is just for these two. We've got infinitely many more in here. How are we ever going to show that if these two cancel, the rest of them cancel? Well, we'll just pair them off. Look at this. Now imagine you come down 1. I go to this one. I consider this wave that makes it over to here. And the next wave down from this other one here. So I move this one down a smidgen, I move this one down a smidgen, and I imagine these two waves traveling a certain distance to get over to this point. What relationship holds between these two? I can do the same thing. These are also w over 2 apart. So this here is also w over 2. So I'd get the same relationship. I'd get w over 2 sine of, is that going to be the same angle? Yeah, it's the same angle, same point on the wall. And this is really far away, so these approximations are hold where these lines are supposed to be approximately parallel because this screen or this wall's very far away compared to the width. That equals, well, that's going to be the same thing. I got w over 2 times sine of the same angle. Shoot, that's got to equal the same thing that it did up here. If the angle's the same, my w over 2 is the same, that's also going to equal half a wavelength. That's also going to be destructive. These two will also interfere destructively, and I can keep playing this game. I can pick this point here over to here and the next one down. These two would have to be destructive. I can pair them off and keep pairing them off. I get destructive for all of them. I could annihilate all of them by pairing them off and finding a partner that's destructive to that one. And so this really is a destructive point. This point over here, all the light is gone, completely annihilated, gives you destructive. So the short of it is that this relationship here, this relationship that W, this slit width, times sine of theta, the angle, same angle we've always been defining it as, equals integer wavelengths. This time, got to be careful though, this time this gives you destructive points, not the constructive points. It was always constructive before. This gives you destructive points now. And you might be upset, you might say, hold on a minute, we only proved this was just for n equals 1 or m equals 1. One wavelength. We didn't prove this for anything besides m equals 1. Well, you can just as easily show that 3 lambda over 2 would also give destructive, or 5 lambda over 2, that would give us all the odd integers here. So m here can be, it can't be 0. We'll talk about that in a minute. It could be 1, 2, 3, 4, 5, and so on. 1 we already showed. 3 you get, well, if you made this 3 halves wavelength, that's also destructive, that'd be 3. 5 halves wavelength, the 2's are always canceling, so 5 halves wavelength would work. What about the even integers? How do we get these? Well, those come from the fact that I didn't have to pair these off with the top one and the middle one. That's dividing this into W over 2. So pairing them off by lengths of W over 2, I can pair them off, I could divide this by any even integer. I can imagine pairing off, instead of doing the topmost one and the middle one, I could do the topmost one and skip one down here. And so I can pair these off. If I divide this into this distance right here, that distance would be what? That'd be W over 4. And so I can imagine pairing off, okay, if these two cancel, if those 2 points cancel, then the next one down, so this one here and this one here would also cancel by the same reasoning. And so I can play the same game now, but W over 4 would be how I divide it. I can't divide it by anything. I can't divide it by 3 or like 2.5 because I always want to pair these off in 2's. Always 2's. That's my whole plan. That's my whole strategy here, is to cancel these in 2's. And I can do that by dividing this by any even integer. So W over 4 would work. What would that give us? Okay, W over 4 is the distance between these, times sine theta, equals, let's just say it's the first one, half of a wavelength. Well, if I solve this, if I move the 4 over, I get W sine theta equals 2 lambda. So the 2's also give us destructive interference. I could divide by 8, that would give us 4. Once I move it over, I can divide by any even integer. Any integer here is going to give us destructive points on the wall. So this would be m equals 1, this would be m equals 2, and so on upwards. So this relationship right here gives you all the destructive points. How come m equals 0 is not a destructive point? Well, m equals 0 is right in the middle. That's the most constructive point. That's the brightest spot. So m equals 0 is not a destructive point, but any other integer does give you a destructive point. So this is the formula for the destructive points. W is the entire width of the single slit. Theta is the angle, the way we normally measure angle here. You imagine a center line like that. Imagine a line up to your point on the wall. This angle here would be theta. And m is any integer that's not 0. Lambda is the wavelength of the actual light that you're sending in here. Now, this just gives you the destructive points. You might wonder, hey, I'm clever. If the integers are giving us destructive points, then the half integers should give us the constructive points. If W sine theta equals, lambda over 2 or 3 lambda over 2, is this going to give us constructive points? And not really. So there's some complications here. And if you're interested in why this does not give the constructive points, I'm going to make another video. Watch that one, because if you've been paying close attention, you should be upset about something else too. You should be upset about something earlier I've said might make it seem like we can prove this does not happen. With the diffraction grating, if you were paying close attention, we proved, quote unquote, that these do not occur. And if you're upset by any of that, or you want to know why the constructive formula does not exactly give you constructive points, watch that video. If you're happy with what we do know, that this gives you the destructive points on the wall, then you're good.